Okay, so hello everyone, and thanks for keeping up to the last day. I know it's not easy with all the stuff you need to catch up with virtually. So I thought a good close up of our mini course was to give you like a perspective, like a big picture of what we have done, and the last touch from today that is going to be a little bit more geometric. So last time, this is probably one of the last pictures we saw, which was the poset of lattice path matrix ordered by the relation being a quotient of. And so I want to do like a summary of the things that we went through so far. And so basically what we started with was we borrowed let's say the notion of linear independence from linear algebra, the notion of bases from linear algebra, and we lifted it up. And the way we lifted it up was by axiomatizing how bases of a given collection of vectors behave, and just capture what the collection of bases satisfies, and use it to define what a matrix is for us. And so the axiomatization leads us to one of the many definitions of matrix, which again, in terms of basis, basically is given in terms of an exchange axiom. And even if we do not pay too much attention to what this axiom says, at least from the point of view of graphs, it's fun and easy to see what the matrix, the graphical matrix we obtain from a given graph. And so just to recall things, here I have my graph with 5 edges, and that means that the matrix that this graph gives rise to is a matrix on the ground set bracket 5, that, remember, this means for us the set 1 up to 5. And the collection B is the collection of bases, which for the graph, it just means the collection of spanning trees. And in this case, these are the 3 spanning trees that we have. And so the ground set, along with this collection of bases, forms a matrix that we call the graphical matrix. And like this example, we discussed some others. And if, again, I encourage you very much, if you have the chance, to take a 1 semester course in basic things of matrix theory, do so. And one of the examples, or some of the examples we also saw, were lattice path matrix, and some others we didn't talk about because of timing and was not really relevant for our mini course. But from the optimization point of view, matrices are also relevant in what is known as the greedy algorithm. Sorry. Or if you happen to take eventually a course on Galois theory and field theory, you will learn about algebraic extensions of fields. And so matrices are also examples in that direction. Or here it should say geometria, or in projective geometry, matrices arise also very naturally in that way. Today, we're going to talk about polytopes a little bit, polytopes from the matrix perspective, or polygons in higher dimensions, if you want. And I mean, this is by no means an exhaustive list. So, and so that was like the starting point, axiomatizing things that we observe in linear algebra, in basic linear algebra. And from the definition of matrix, then we started exploring like a little bit more what happens from the linear algebra point of view, and again, try to lift it from the matrix perspective. So the other thing that we did, or we observed, was if I take this 3x3 full rank matrix, that from the linear algebra point of view just means you are taking a vector space, say the vector space spanned by these 3 rows, that's a 3-dimensional vector space. And then what you do is from these three elements that form the basis for a basis for your vector space, you drop the last one. So you're left with a two-dimensional vector space. And from this one, you drop the last one. So you're left with a one-dimensional vector space, though, so that forms like a sequence or chains of vector spaces that differ by rank in one every time, by dimension. And again, so we want to try to think of how a good axiomatization of this phenomenon, or what does this mean, this deleting rows from the bottom to the top means from the matrix perspective. So axiomatizing this means provide a definition that captures what happens here and that can be used in the matroidal sense. And that axiomatization leads us to the definition of what a quotient is. And again, in matrix, you will always find that there are lots of definitions for many of the things that we work when we work with matrix. And this definition that we provided here was by saying that a matrix M is a quotient of a matrix N if every circuit of N is union of circuits in M. So that's what I wrote here. And again, graphs are a very good example because they are very, let's say, tangible to work with and easy to manipulate, at least to work out some examples and getting used to the definitions. And again, for us, circuits on a graphs are these closed paths without visiting a vertex more than once, except the beginning one, the initial one. And so here, this circuit, we should be able to write in terms of unions of circuits here, which we can do by just writing these three sets of edges as the union of these two and these two. And so that is one of the definitions that we used here. But one of the things that we pointed out was that the larger, for instance, in the case of graphs, the larger our graph is, the harder it is to try to say prove or imply that somebody else is a quotient of a given graph or of a given graphical matrix. So this definition is a definition and it works, but it has like its difficulties. And so what we wanted was to try to understand from let's say more combinatorial perspective, or maybe in a more easy way, if possible, this definition, at least for some families of matrices. And that's what we did last time. So we wanted to provide a characterization of being a quotient of for the family of lattice path matrix. And I want to recall how this worked. We did some examples, some exercises about this last time. And what we said was the following. Again, if I call this guy N and this guy M, the definition would tell me for M to be a quotient of N. So in this case, it is true. And according to the definition, I would need to compute all the quotients of N, which is going to be not easy. And each of the quotients of this matrix, write it as union of quotients of this matrix, which again, I'm not working with graphs anymore. I'm working with another family of matrices. So computing circuits is not going to be as visual or graphical as in the case of graphs. So here the characterization we provided and I showed to you was the following. In order to conclude this, so what needs to happen? What needs to happen is that, so recall that here I have these labels that give me my upper bound of the lattice path matrix N. And the labels from the upper bound we called U, and the labels from the lower bound we called L. And so the only thing that we noticed was on the first place, let's say the labels on the upper boundary of M are a subset of the labels of this guy U here And in this case, actually, they differ only by one element. So here, U prime is obtained by U removing 10. So here I'm gonna mark 10. And similarly, L prime, so the lower boundary, is obtained from L by deleting one label as well. And the label we deleted in this case was 8. And so given this, how can I conclude that actually M is a quotient of N? I can conclude that because when I take this step, which is actually the one I end up deleting. So if I look at this region, so if I look at the region in this portion, so I just draw a vertical line containing the U step I'm deleting and a horizontal line that is kind of touching the endpoint of U here. And this region, or within this region, any of the labels in L that appear, I'm able, or I can choose any of them to delete along with U. In other words, in this case, the matrix M that I obtained, which was by deleting 8, is good because 8 is in the admissible region, let's say, determined by 10, okay? But again, another one that I could have obtained, say a matrix M prime, which is going to be also a quotient of, let's call this double prime. Also a quotient of N is, say, for instance, if you were to choose the same 10, so you're going to delete 10 out of the labels in U, and say instead of 8, then you choose 11. That is also going to be a good pair, an admissible pair that you are able to delete in order to produce a quotient. So you see that in this case, the label 10 provides you 1, 2, 3, 4, 5, provides you 5 different coverings or 5 different matrices that are a quotient of N. And if we do that with each of the north steps, so we are going to obtain a bunch of matrices that are a quotient of N. And so this is a characterization that does not appeal to the circuit definition. And it's as easy as it could be. And so that's the thing that we ended up with last time. And I want to know if you have any questions before we continue. All good? And it's also okay to receive confirmation either by chat or using the microphone, but I do need confirmation or not. Oops. Okay, thank you, Abril. Yeah, when I use the tool for annotate, I'm not able to go to the chat or anything like that. So anyway, okay. Okay, good. So as I said, the last tool that we are going to introduce today, and it's actually what the exercises are about, is a geometrical tool. So what are we going to do? We're going to think of these sequences of matrices as we had before. We're going to think of these sequences, but in the case of Lattice Path Matrix, so we're going to think of these sequences of Lattice Path Matrix as polygons. And so let me show you how we're going to do this. So here I have the picture that allows us to think of each one of these chains as a polytope. And so I'm going to show you an example of how this works. And the purpose of the exercises today will be to actually compute as many of these polygons as you guys can, okay? So it's very important for me if you let me know that it's understandable or not, okay? So let's take, I don't know, let's take maybe this chain here. I'll take this chain here. and this, okay? And so in the right-hand side, it appears here. Okay, so it's this one. So I want to convince you that this chain is actually this quadrilateral here. And so what I'm gonna do is I will tell you what these vertices are. And that's basically what we're gonna do, okay? So you see that, oh, actually I took the wrong one. I had chosen this one, and it's here, this one. Okay, this is the right one.
Sorry, I read the question by Ashley. She said if it is because it's in the chat, if it is the third set.
Yes, yeah, I had chosen the wrong one. Thank you. Yes. So it's this one here. Okay. So you see that I'm kind of ignoring this bottom element and this top element. And I'm gonna ignore them also because for each chain, the bottom and the top is the same. So basically I can just codify this chain by these two elements that appear in rank 1 and rank 2, or that appear in the middle, okay? Okay, so how am I gonna produce this polygon here? So actually, I'm gonna probably draw this here. Oops. So this is this guy, and is covered by this guy. And so I'm gonna label the U and L, so the upper boundary and the lower boundary for each one of them. So in this one, the upper one is 1. So only have one label, which is the first step, and that step is north, so I label it 1. For the lower one, I have to label this guy. And how do I label? So I just count what step is this. 1, 2, so this is 2. And what would be the labels for this one here? I start working from here, and so what would be this first label? You can reply in the chat or unmuting yourselves. It's the question clear, or is not too clear? What do you think? So can you hear me, or?
Yes, yes.
Okay, so let me repeat the question. I need to label these steps, okay? How do I label them? I start walking, and as soon as I see a north step, I label it with the step that is being used, okay? So this first one going north, being the first step, is labeled 1. And this one, what is its label? Jeronimo, help me out with the chat. I cannot see it.
He says 2.
2. Good. Okay, so now let's move on to the lower boundary. So I'm not using the first step. So the first label is going to be this one, which is what?
One.
So this is 1, but this is 2. Okay. And how about this one?
3.
3. Okay. So it's very important that you guys know how to label this, because the exercises are based on that. And so the first step is to be able to label the steps in a lattice path matrix. And basically, again, what we do is start counting. As soon as I see a north step, I label it according to what step is it. If I start here, so from here I start my counting. If the step I'm looking at is north, I label it. If the step I'm moving over is not north, I do not label it. Okay, I just label the north ones or the vertical ones. Okay. And so now that I have my labels, so what we are gonna do, and maybe just to confirm, let's include the last one, which consists of these 3 guys. Okay. And so the labeling of this one, so on the left side are the labels of the upper portion, and on the right hand side are the labels of the lower portion. And I start walking always from here. Okay. So in this case, all my steps are north or vertical, meaning the first, the second, and the third step are part of my upper boundary. And similarly for the lower one, the first, the second, and the third are also that. Okay. So here we have already the labels. And now in order to build this guy, this polygon here, so this is what we are gonna do. So I will call this M1, this M2, and why not calling this M3, okay? And so M1, I'm gonna write down explicitly what its bases are. And remember, for us, the bases are just the paths that go from the southwest corner to the northeast corner of your diagram. And so all the paths that are within this region, paths that are either using vertical or east steps, and then we just record the labels. So one way to do that is going like this. And if I go like this, I just record the north labels. So one basis is 1. So that's one option. Another option is if I were to, in this case, I do not have too many options. I can do like this and like this, and I just record the north label, which in this case, that corresponds to 2. So in this case, this matrix is kind of simple. It just has 2 bases. And I'm gonna do now the same for B2, for M2. I'm gonna write down the bases or the paths that allow me to travel from here to here. So I'll draw this one here. So U is always one way. So starting from here, going all the way here. So recording the north labels, I get the set 1, 2. Now I can do what else, for instance?
2, 3.
So I can do, so if you start from here, so maybe you can
Right.
start telling me, go right, okay?
And then up and up again.
Exactly. So going right and then up and up, I just record the up steps. And so in this case, my basis is 2, 3. Is there any other way I can walk from here to here, remaining in this area that I could use to build a path?
Maximiliano says 1, 3.
So Maximiliano says, start from here, go north east, north. And if I go north, east, north, so I end up recording 1 and 3, okay? And I have no more options in this case. These are my only possibilities. So these are my 3 bases for this matrix. And for the last one, there is only one way, no? To go from this dot to this dot, there is only one way, which means this only has 1 basis, and that basis consists of the set 1, 2, and 3. Okay, so you see that this sequence actually is such that the first matrix has as basis subsets of size 1, the other one has basis subsets of size 2, and the last one has basis subsets of size 3. And that's going to happen if we were to enlarge our ground set. Similarly, as we were deleting rows in the matrix, we started lowering dimension by 1. And so this is like the analog to that. Okay, now I have my collection of bases. And what am I going to do now? I'm going to start building chains of bases. So now I'm going to build chains of the bases. Okay, so that means I will take, for instance, this for each basis of this guy. So for instance, if you start with 1, so 1 is a subset of which ones here? 1 is a subset of 1, 2. Okay. And also a subset of 1, 3, but it's not a subset of 2, 3. And so now I look at this chain, and this chain or this subset 1, 2 is containing 1, 2, 3. And similar 1, 3 is containing 1, 2, 3. So here I have a chain of bases, and this chain of bases uses the element 1 from the first one. And now I have to do the same for 2. So can someone tell me one way I can put 2 inside the second matrix?
Two is contained in 1, 2.
Exactly. And it's also containing 2, 3. And each one of them is containing 1, 2, 3. So these are all the chains I can build from my bases from the first, the second, and the third. I cannot do any other containments. I exhausted them all. And the fact that we have 4 chains is actually corresponding to the fact that here you see we have 4 vertices. So what are these vertices? These vertices are actually the following. So now what we are going to do is this triple of subsets, we're going to think now as a vector in R3. So what vector is this going to be? So this is going to be the following. It's going to be 3 stuff. What I'm going to do is basically I will put the numbers 1, 2, and 3 in some order here. Why 1, 2, and 3? Because one of the elements, 1, 2, 3, is repeated 3 times. Another one is repeated 2 times. And the last one is only repeated 1 time. So basically, I'm going to count repetitions, and those repetitions I put here. So we notice here that 1 is repeated in the 3 subsets. So the first coordinate is assigned 3. 2 is repeated only in 2 subsets. And 3 is repeated or appears only once. Okay, let's do this one. Again, here I will assign a triple and just record the repetitions of each element. So the first one appears how many times?
3.
3. How about 2?
1.
1.
And 2.
And 2. Actually, here, when we're doing this recording, we're going to have no repetition. So what we will end up with is a permutation of the elements 1, 2, and 3. How about this one? Here also we will have a triple. And the first element is repeated how many times?
Maximilian says 2.
2. How about this guy?
Again, he says 3.
And the last one only appears once, cannot appear nor 2 nor 3 times. And finally, this one here also, this is the first one that shows up. This is the one that shows up next. And one is the last one that shows up. So here are my 4 elements from R3. And if I were to plot them, I end up with this guy here. So to make the life easier, so basically, I will draw how you would see the 6 permutations on 3 elements. How would you see them if you were to plot them in space? Either if you use GeoGebra or Desmos, if you are familiar with them. But basically, if you were to plot them, I'm gonna now ignore the commas and just think of the triples without commas. So for instance, this one here, I'll put here. Here on the other extreme, I'll put 1, 2, 3. Here I'll put, hold on, I'll put here 1, 3, 2. I'll put here 2, 1, 3. Here 3, 1, 2. And here 2, 3, 1. So this is the 6 ways of arranging the numbers 1, 2, and 3. So these are the 6 permutations, what we would call permutations of 1, 2, and 3. And again, if you were to use any software to draw things in R3, or if you were to do it by hand, you will see that these 6 points in R3 actually draw like a hexagon. Okay. And I'm just gonna throw these 2 lines here because really this picture here, even though it has 2 extra lines that before the hexagon didn't have. Basically, this picture here is what we know as the Bruja order on permutations, but it doesn't matter too much here. The point is then that with this picture as reference, now let's locate these 4 points we obtain. So I can see that here is one of them corresponding to the first one we computed. And this one we see that appears here. This one appears here. And this one appears here. And we see that in our reference picture, what they draw is this quadrilateral. And again, if we were to plot these 4 points in space, you will see that they draw a quadrilateral, okay? And so this is what this thing on the right-hand side represents for each one of the chains of my saturated chains on the POSIT. Do you have any questions? Okay, because again, as I said, it's important to solve them now because the exercises are based on this. Okay, good. So that's what we are going to do now. We're going to break out in groups and work out there is basically just one exercise, and the exercise is for you guys to actually show that each saturated chain from the POSIT on the left-hand side corresponds to the polygon that is given on the right-hand side in this picture here, taking as reference this big guy, okay? So that's basically what the exercise for today is. And so we're going to work on that for a while. Then we will come back here again for some final remarks and